Good afternoon, everyone. I'm Christy Risk, Senior Editor at GenomeWeb, and I'll be your moderator for today. The title of today's webinar is Applications and Challenges of Using ctDNA as Non-Invasive Tumor Markers, and our sponsor is PerkinElmer. Our panelist today is Dr. Alexander Sartori, Manager of Scientific Affairs in the Europe, Middle East, and Africa region at Agena Bioscience. You may type in a question at any time during the webinar. You can do this through the control panel, which usually appears on the right side of your screen. Click on the Q&A box on the upper right side of the control panel. When you click on Send To, please select All Panelists. We will ask the panelists questions after the presentation has concluded. Dr. Sartori, please go ahead.
Yes, thank you, Christy, for the kind introduction, and many thanks to GenomeWeb for realizing this webinar, and to PerkinElmer for the invitation and opportunity to speak to all of you today. So, hi everyone. That's the title slide, and that's my disclosures. In this session today, we will learn about how ctDNA as target for liquid biopsy analysis can be controlled. So you no longer need to worry about the putative complexity of this application. And we will see examples on how analysis for a panel of markers can be achieved from just a single precious blood sample. Before we start, just a couple of words about the company I work with, Agena Bioscience. Well, our mission is to empower the translation of genomic discoveries into mainstream clinical practice. And to do so, we are working, or we have a number of clinical and non-clinical applications around the MassARRAY system, which is a MALDI-TOF-based mass spectrometer. And more than currently 4,000 scientific publications prove the feasibility. Sorry, I'm just getting. Can anyone hear me? Sorry.
Yes, Dr. Sartori, we can hear you.
Okay, because sorry, I just saw a message from. Okay, that's good. Thank you. Thanks. All right. All right, Bex. So more than 4,000 scientific publications prove the feasibility of the MassARRAY system. Agena Biosystem is headquartered in San Diego, California, and we have offices in Australia, China, and Germany. Basically, our main and focus applications are, as today, oncology and liquid biopsy, but also pharmacogenetics and sample identification. So today, I'm speaking to you from Hamburg, Germany, as you may hear from my accent. So, when talking about liquid biopsy, it makes sense to start with the status quo of oncology testing and its limitations. So one being the sample quantity. As you see in this picture of a lung thin needle core biopsy of adenocarcinoma, so of a non-small cell lung cancer, it's the large cells that we're looking for, and in this tiny little bit of tissue, there's just a very small number of tumorous samples. So that is one limitation. And another limitation is the sheer availability of tissue biopsies. In this recent article in The Pathologist from February this year, the author summarized that too many lung cancer patients experience needless treatment delays because the genetic data arrives too late. And that may be due to the technology being used for the analysis. Furthermore, in 30% of lung cancer cases, no genetic information from a tissue biopsy can be achieved. May it be because of the procedure is too risky to do, or that the tissue biopsy provides too little tissue, too little material. And in addition, it is a highly invasive procedure, and physicians are reluctant to perform multiple biopsies. Well, not just reluctant, but simply sometimes it's not possible. So, so it's nearly impossible using a tissue biopsy to monitor a treatment of a patient. So the conclusion of that article is that that too many patients who are ineligible for tissue biopsy can still undergo liquid biopsies. Well, another limitation is the tumor heterogeneity. So when taking a tissue biopsy, we usually only target a single clone and are able to interrogate the mutational profile of that single clone, whereas that tumor may be composed of various subclones that you can't interrogate from a tissue biopsy. So taking all these limitations together, again, which is limited sample quantity, highly variable sample quality, the tumor heterogeneity, the problem of or the problems of the invasiveness of taking a biopsy, and the fact that we may have to deal with a metastatic disease where there is a remote site shedding or being tumorous, and couple this with the desire of today's desire not only to interrogate a single marker but multiple markers at the same time. Well, all this taken together is a great opportunity for multiplexed mutation detection in liquid biopsy to go into the clinical routine. So maybe we should step back and discuss and define what is a liquid biopsy. Well, by definition, liquid biopsy is sampling and analysis of non-solid biological tissue, primarily from blood. Initially, the term was used or started to be used for circulating tumor cells, CTCs, but is also commonly used now and more for cell-free DNA, for cell-free RNA, cell-free microRNAs, and exosomes. And today, we will focus mostly around or exclusively around cell-free DNA, which is also abbreviated with cfDNA or even ccfDNA for circulating cell-free DNA. Well, and that cfDNA represents all cell-free DNA in the body, in the bloodstream, being shed from the tumor by apoptotic and necrotic effects or mechanisms. And just a tiny little subset of the cfDNA is the so-called ctDNA or circulating tumor DNA, so the mutant species. So it can be as little as 1 in 1,000, so as 0.1% of the entire cfDNA. So usually when talking about cell-free DNA, we think about blood being the basis. And as you can see on the left-hand picture, well, the fragments are short of cfDNA, and we will cover the size of these fragments a little later in greater detail. However, blood is not the only possible source. You could think about sputum, urine, or maybe pap smear, as you can see in the screenshot below, which can be used as a source for liquid biopsy, if that makes sense. For urine, for instance, if you think about bladder carcinoma, well, that could make a lot of sense. Well, it's certainly, I mean, there's a lot of literature that gives us evidence that the pure level of ctDNA can be used as a predictive marker, so that ctDNA has its justification to be used as a marker. In this plot, we see the difference between in progression-free survival for subcohorts of patients, where in the blue line ctDNA is not detectable, which gives us a better prognosis than for those cohort or for those patients where there is detectable ctDNA in the blood. If you think about the abundance of cell-free or circulating tumor DNA in various solid cancers, well, here you see a representation of a few of them, where two typical examples, colorectal cancer and breast cancer, are highlighted with these arrows. So there's a number of solid tumors that have where a very high frequency of patients for a very high number of patients, ctDNA can be detected, whereas at the right-hand side, towards the right-hand side of this graph, there's a few tumors where ctDNA can be, well, was shown to have low abundance, for instance, glioma or thyroid cancer. Well, maybe it's time just to think a little bit about why these fragments, why these CF or cell-free DNA and circulating tumor DNA molecules, so cfDNA and ctDNA molecules, are so small. Well, it's just explainable by the fact that the DNA, when surrounded or wrapped around the histones and undergoing apoptosis, for instance, are being fragmented at the free ends, and the length of a wrap around histone octamer is 160 base pairs, and consequently the peak of ctDNA and cfDNA fragments is in the range of 166, 167 base pairs, so that's where the peak is. Well, we do have a few shorter and longer fragments, but the majority are in that range, so that mechanism can be easily explained. So when we start working with, or consider working with cfDNA, ctDNA as a marker in liquid biopsy, we should consider a set of pre-analytical conditions and a proposed, well, and the obvious steps that need to be followed and should be taken into account are the steps from 1 to 5 in this graph, in this flow chart. So it's first the decision that one has to make on blood drawing, on which tube to be used. Well, and then if we have blood, well, there's a time dependent component, but actually the next step certainly then is the plasma centrifugation, so the centrifugation to obtain the blood plasma that contains the cell-free DNA, which in the third step need to be isolated and concentrated. And at that stage, and before entering any precious material and any low abundant DNA material into the liquid biopsy analysis, in step number 4, it makes a lot of sense to perform a QC step to make sure that you don't have any contamination and that you have the desired material in the required amount. And then in number 5, it really comes to the actual analysis of the precious sample. So we'll talk about all of these steps in a little detail. So going back to the first step, which is the blood drawing. Well, the most commonly used tubes are the EDTA tubes that are around in the clinics all over the world. Well, their advantage is that they are commonly used and easy to get. So it's actually not a problem to use blood or blood plasma from EDTA blood. However, the drawback is that it bears a high risk of contamination with genomic DNA due to the potential lysis of white blood cells, especially if it takes a long time or longer time before you can further process the sample. So if that process cannot be controlled properly, as we will see on the slide after the next. An alternative to that is using special tubes for the collection, or for the collection of blood for use of cfDNA. So special cfDNA blood collection tubes, which are, for instance, provided by companies like Streck, Roche, or QIAGEN, and many more. So there's more providers coming to the market with these special tubes. A statement from Streck, just because they were one of the first offering such a product, you can see in the red rectangle text, is that, well, this is a blood collection tube which stabilizes nucleated blood cells. Its unique preservatives prevent the release of genomic DNA, so that is what we want. We don't want genomic DNA to dilute our cfDNA and allowing the isolation of high-quality cell-free. So that works very nicely for up to a number of days, depending on the very tube that you are using. In this case, it's 14 days at room temperature that you can store your blood. So, for instance, if you think about drawing blood at a remote site, far away from the hospital, from the clinic, where the analysis should take place. Actually, at the AACR conference starting next week in Chicago, there is a poster that I am aware of that takes the comparison between EDTA blood and the use of special tubes into account and compares the two methods. That is poster number 5596 at AACR. So just a side note, I was already mentioning plasma as a term. Well, sometimes we get questions about can we use serum versus plasma, and the clear recommendation in the literature and from people working with liquid biopsies is to use plasma as a source. Well, ctDNA is also contained in serum, but this can be highly diluted with non-cancerous DNA, like genomic DNA. That, again, is what we want to avoid. So if we talk about ctDNA, we equal this being used from plasma. So after the blood draw, the next step being the plasma centrifugation. And I'm not going through the details of that protocol. There's a number of very, very similar protocols available in the internet. So this is just one, but if you compare them, they are very, very similar. Basically, you perform the dual high-speed centrifugation, where that separates the solid components of the blood from the liquid components, and the liquid component equals the plasma, and that contains the cell-free DNA components. Again, it is cfDNA as a majority, and a very little fraction is the ctDNA, so the tumor-related cell-free DNA, or this circulating DNA, so the ctDNA. Actually, as a side note to that plasma centrifugation slide is that, well, as I said initially, you can obtain very, very nice results from using EDTA blood. That is the first green bullet point here. If it is guaranteed that your centrifugation, as shown here, can be performed within 2 hours with the blood being stored at room temperature. So if it takes longer, then we would advise, or it is advisable, to use special tubes. So going to the third step, the cfDNA preparation, so the isolation of cfDNA from the plasma. Well, that is something I just want to bring to your attention, that there is a number of providers and kits available, and I don't want to recommend any over the other. So that's a long list. It's probably not even a complete list. And what we do in scientific affairs at Agena, we receive a lot of samples from collaboration partners, and basically there's a number of kits that provide high quality cfDNA. So again, there's nothing I really can and want to recommend here, but there is a reference at the right-hand side, for instance, that deals with various of these, with the differences and different qualities of various of these kits. Well, first step achieved, I think. After having isolated the DNA, we certainly hope to have fragments of the desired length in our tube, so being fragments that peak at 167 base pairs or in that range. But how can we know? I mean, is it a good idea just to enter that isolated material into your liquid biopsy test? Probably not, because that's something that cannot be repeated, as we said. Probably the result of a blood draw that you cannot easily get well drawing blood can be repeated, but certainly not of that status or of that very sample. So it is advisable certainly to think about quality control of your sample, of your cfDNA sample. Well, and here you see a couple of examples why quality controlling is a good idea. So you can assume having a good sample or not so good sample, or even something that you don't want to have. So in the top panel, you see target fragments of the desired length. Actually, the second peak to the right-hand side is a marker, so don't worry about that one. Is a length marker for the sizing. So the peak to the left is what we desire to see. And it has, on the first glance, it has a nice height. So probably that's a good sample. Well, the sample in the middle may even be a good sample, but it's very, very little. There's very, very little cfDNA, so maybe a sample to be avoided or to be omitted just because of its low concentration. And then last but not least, the sample, the example at the bottom represents, well, there is cfDNA, but there's something else. There's probably a contamination with genomic DNA, and that is a sample that you probably want to skip as well. So these examples were made with the lab chip from PerkinElmer. It is a microfluidic capillary electrophoresis system, and actually its DNA 3K assay is specifically suitable for the measure for the QC of cfDNA. The nice thing about it is that you can do both sample integrity and concentration measure from just a single microliter of precious sample. And consider if you only have 20 microliters, in the range of 20 microliters, it is good not to use too much for it for the QC. Well, it also can quantitate. We come to that point just in a minute by defining a region of interest underneath the smear, underneath the fragment size of interest. As you can see by the line underneath the bold part of the curve. So why do we need to worry about not just about sizing, but also about the concentration and the amount of DNA? Well, if we take a look on the sensitivity, on the analytical sensitivity that we need to achieve when working with liquid biopsy, then this makes a lot of sense. So going maybe a little step backwards, going to the conventional testing of tissue, well, then an analytical sensitivity of greater than 1% or even 10% is not a problem, as it can be achieved with real-time PCR, NGS, or even Sanger sequencing. But when you go to the lower half of the image, so when you want to perform analysis of liquid biopsy, well, then, as we said initially, due to the high amount of non-tumors, so wild-type DNA in your sample, and just the low fragment or the low percentage of CT, so tumor-derived material, well, you need to achieve a sensitivity well below 1%, probably in the range of 0.1% or even lower. So here, for that purpose, you can use various technologies, and I'll give you a little bit of a technology overview a little later. But certainly, you want to make sure you enter enough copies or molecules into your reaction. So the relation between input amount, detectable mutants, and sensitivity is beautifully displayed in this table. So in the green part, actually, when starting from the middle, from where you can see the number 3. So number 3 represents well, a low number of mutant molecules that you want to be able to detect. But this being ctDNA in a high background of cfDNA, you can assume that these 3 molecules are in a pond basically 1 in 1,000, so maybe 3,000 total copies of DNA. So 1 in, or 3,000 in, well, 3 in 3,000 equals 1 in 1,000, and that so that is the sensitivity that we need to be able to achieve is equals 0.1%. And luckily, well, these 3,000 copies is the number, well, is the amount of DNA that equals round about 10 nanograms, or equals 10 nanograms of DNA, and that is what you typically can achieve from a single blood draw. Well, that is a realistic amount and typically achievable in a clinical situation. So when then provider of a technology claims to have a higher sensitivity, and there's technologies that can go lower, well, then this equation is illustrated by the yellow boxes and arrows. So a sensitivity of 0.01%, for instance, means that being able to detect a low number of mutant alleles or mutant molecules in this example, so 3 mutant molecules would be diluted by 30,000 total molecules of DNA, and that would require 100 nanograms of input DNA, and that certainly cannot be achieved from a single blood draw, then would require multiple, so in this case 10 blood draws, which is probably not very practical and realistic in the clinic. So I think we understood why not just sizing, but a proper quantitation is also required, and the lab chip that I introduced to you earlier, well, does the two things at the same time. In this example, you can see that it's undiluted. Well, that calculating back this sample to the undiluted concentration has 0.86 nanograms per microliter, for instance. So that is a good amount. It's really a nice amount to be working with. As you can see here in a table from a real study that we did recently, is that first, if you compare just quantitative measures from the qubit with a lab chip, that they both do pretty similar for most of the cases. But I want to highlight the case number 5 here, where the qubit, for instance, was measuring a much higher concentration than the lab chip, and well, the qubit is blind on the sizing side. So for getting this information, you would need to use a second technology. The lab chip actually, and this is the nice thing. This is the very nice thing about it. Also provides you with the sizing information. So what we could see is, well, this is a sample that is highly contaminated with genomic DNA, and that we would probably like to omit, to reject from our study, because it only has not only a much lower amount of ctDNA, but well, it has this monstrous amount of genomic DNA. Another example is probably the clean example. Well, the electrophoregram is not shown here, but this is a clean sample that has a concentration of half a nanogram per microliter. And in order to, just to give you an idea on how this works, so in order to achieve our 10 nanograms of DNA going into our initial analysis, we then would have to take 20 microliters from that sample. Well, then there's technologies that don't have that volume for 20 microliters, but I'll come to that in a little. So I promised everyone a little bit of a technology overview on what can be used, what technologies are commonly be used for performing liquid biopsy testing. And this is certainly not exhaustive, and it is probably also simplifying things a little bit, because, well, under each column there's a number of providers, and I don't want to be really too detailed here, just to give an idea. So, well, on one hand, digital droplet PCR is commonly used and mentioned when it comes to liquid biopsy testing. And at the far other end of this spectrum, well, you hear a lot about NGS. And you simply from looking at a few categories that are listed here, like ease of use, time to result, multiplexing, number of targets, mutation detection, sensitivity, cost, data analysis, etc., that there's that NGS has a huge advantage, and that is it's not just a targeted approach, certainly like the other two technologies, digital droplet PCR and the mass spectrometer, but it also can do de novo, and thus it's perfectly suited for discovery purpose. But there's a number of categories where NGS may appear to be a little complex. The workflow takes certainly longer than for the other technologies. Sensitivity is not in the absolute desired range unless you drive the coverage really, really hard, which again drives the cost up. And then a big concern of many is the complex data analysis, where for NGS you require a little bit of experience in bioinformatics, where for the other two technologies you don't. It's the allele calling is just happening at the detection. Well, digital droplet PCR, at the other hand, is fulfilling a lot of these features beautifully, but you have to understand that it has no multiplexing capability. Well, you can interrogate a single or two markers with one sample, but not more than that. So you may not have heard about mass spectrometry being used for nucleic acid analysis too much, so maybe I give you just a little bit of an overview about that technology, so to complete that picture. So the MassARRAY that Agena is providing is, well, it's based on a multi-TOF mass spectrometer, exclusively being used for nucleic acid analysis. And the way it works is that after a conventional PCR, the interrogation of the mutations is done by a simple primer extension reaction. And the fact that the incorporation of either a wild type base, like indicated in the left panel, in the left pane at the top, so the incorporation of whether of either wild type or mutant, here symbolized by the G in blue or the C in green, this results in reaction products of slightly different mass difference. And the mass spectrometer is accurate enough to measure these differences and to accurately call this the left reaction product the wild type and the green one a mutant. So that is the underlying principle, which is the wet lab part. That's the only wet lab part that you have to do. It's just a PCR-based primer extent-based reaction. The rest is being done in an automated fashion. The rest is just spotting the reaction product onto an inert silica chip that is then being automatically transferred into the detection chamber and detected by the mass spectrometer. Well, and then as mentioned, number C here is then the automated data analysis. So at time of detection, you will get your allele calls, and certainly then automated reports will give you more information about detected mutations and confidence value. Another important aspect that I mentioned earlier is that if you have low concentrated cfDNA, like in that range of 0.3 nanograms per microliter, for instance, then the equation would require you to use more than 20 microliters of input material into your reaction. And here at Agena, what we do is our initial PCR. So we start from a single PCR, and the initial PCR volume is 70 microliters, so you have up to 35 microliters for your sample. So even a low concentrated sample can achieve enough DNA, these 10 nanograms that are required for your 1 in 1,000 limit of detection. So then we use aliquots of that PCR, various aliquots of that PCR for the interrogation of the mutations in the subsequent single base extent reaction. But enough about technology. it is time really to talk a little bit about some applications and some examples on where liquid biopsy can make the difference. Well, going into non-small cell lung cancer and study or a clinical trial that may be common or known to many of you. So in that clinical trial, AURA, it could be demonstrated that in principle, the detection, well, first I should say that in non-small cell lung cancer, there's a very more and more famous resistance marker in the EGFR gene called T790M. So that resistance marker, well, it is important to monitor that potential resistance because it is resistance against the first and second generation TKI treatment. So you want to know if that resistance comes up. So in that clinical trial, it could be shown that that T790M can be as good, can be detected as good from solid tissue than from plasma, so than from liquid biopsy. And so this marker was the first one that became an FDA recommendation to be used in liquid biopsy to start with. So, so this is the first case where the recommendation said start with a liquid biopsy test, test for T790M, and if it's positive in liquid biopsy, you can skip the tissue biopsy and start with your third generation TKI treatment, so which is the advised drug when this resistance is being observed. But only when your liquid biopsy test is negative, then it is advised to go ahead with the conventional way with a tissue biopsy. But this will certainly mean a relief to many, many patients that don't have to go that tissue biopsy initially. So the importance of the relevance of that T790M marker, well, made a couple of authorities and a couple of activities to become so to have pathology labs to be able to show that they are able with their technology to detect that marker T790M. And here there's one example of a ring trial, of a round-robin trial that was performed in Germany in 2016 about the detection of T790M, sending 10 blinded tissue and 10 plasma samples to the participating labs. And in the article at the bottom, you can see the results of that study and which technologies performed well and which not so well. And at the right-hand side, well, you can see an example of how a 0.1%, so the limit of detection, result on the Agena lung panel looks like for T790M, and how easy it is to distinguish from the clearly negative wild-type sample. So this is how a result looks for mass spectrometry, for instance. Well, but it is not enough, in the opinion of many authors and scientists, to just detect the T790M marker. And here's why. In this graph, well, you do see a blue line which shows the progression-free survival of patients where the T790M marker could be detected. But then you see two yellow lines where the lower one actually represents the cases where T790M was not detectable, but if you co-detect a number of sensitizing mutations, so activating mutations in the EGFR gene, so these are detectable, these sensitizing mutations, then this means a completely different pattern for the progression-free survival, and I mean a worse prognosis to these patients, then if you compare that to the case at the top, where T790M is negative as well, but where you could not detect sensitizing mutations, that simply means that there was no ctDNA detectable in these patients. So the difference between T790M being negative can mean it is negative, but there is ctDNA, or it is negative because there's no ctDNA. Well, and the paper cited at the bottom gives you more detail on these facts, and there's a number of other papers working on the necessity of interrogating a larger panel of mutations at the same time. Well, if we then go back to the technology that was listed in this technology comparison, digital droplet PCR, well, here's a consequence of what testing multiple markers with digital droplet PCR, for instance, the sensitizing mutations and the resistance markers. So due to the lacking ability to do multiplexing with digital droplet PCR, then again it would mean a single blood draw or a single sample wouldn't be sufficient to fulfill that task, but you would be required to use multiple blood draws. Well, following the recommendations of analyzing a panel of markers, this is just a snapshot of the lung panel that Agena offers. Certainly, a lung panel or a non-small cell lung cancer panel is very EGFR-centric. It certainly has all the sensitizing mutations and the resistance markers, and it has content in BRAF, KRAS, ERBB2, and PIK3CA, just following the international guidelines for the interrogation of markers in non-small cell lung cancer. And all these 67 markers can be interrogated from a single starting multiplex PCR, as I alluded earlier, with the limit of detection down to 0.1% mutant allelic frequency. So when we came out with this panel, we were very lucky to work with the University Clinic in Hamburg that is being led by Professor Klaus Pantel, who is a very important scientist in the area of liquid biopsy. So Klaus Pantel and Harry Wigman from the same institute provided us with ctDNA samples about which they were suspicious that well, anything can be detected in ctDNA, just because it was from a cohort from lung cancer patients that most of them developed brain metastasis, and well, at the site of drawing the blood, well, the tumor was represented by the metastasis in the brain. So the hypothesis being there's a brain-blood barrier, and it's probably very unlikely to detect any ctDNA. We were getting these samples, and as you can see in this table, we were not only able to detect, to confirm the majority of EGFR sensitizing mutations that initially had been detected in tissue before the therapy started for these samples or for these cases, but due to the fact that our panel offers more than just EGFR mutations, but also KRAS content, for instance, we were able to detect, and that you see in blue in the right-hand side column, we were able to find mutations that were not known previously. And in addition, due to the very interesting example is the case number 11, where over the course of the therapy, resistance has occurred, like the T790M resistance marker, and we were able to detect it at very low allelic frequency. So this was in an initial study starting last year, but it has grown over time. And at AACR next week in Chicago, there will be a poster about that extended study, and that will be poster number 4614. If you want to get some more, if you have the chance to go to attend AACR and see that poster. Another exciting study in liquid biopsy is, well, I spoke about, usually you talk about, you think about blood or plasma being used as a source, but in that very study that you see here in front of you, that we did with the RCSI in Dublin, Ireland, with Professor Brian Hennessy and Robert Smith, we were able to detect, or the idea, let me phrase this differently. The idea was, well, can we use something else than blood? Can we use the breath of a lung cancer patient? Well, that is a fascinating idea, and certainly you cannot take the breath because it's airless. But if you condensate the breath and get a condensate using a special device, it's a tube that has a freezing element. So if you condensate that breath, you get something that is called the exhaled breath condensate, or abbreviated EBC, and actually we were able to detect the T790M resistance marker from that EBC in the control, so in the cohort where we were expecting the marker to be present, as good as in plasma. So these numbers suggest that EBC detection was better than a plasma, but you see the numbers are very low, and also this study got extended. But I can confirm that, very exciting, the detection of T790M in EBC is as good as in plasma, and that was exciting a year ago at ASCO, where this work earned a Young Investigator Award, and the study got extended and will be presented at the ISMRC in Montpellier in France in May as a poster and as oral communication. If you are, well, lucky enough to go to that conference in May, so this is a prestige liquid biopsy meeting, a meeting that is being organized by Professor Klaus Pentel and others in Europe, but which has a, as you can see here by the confirmed speaker list, which has a very international composition and is very prestigious. So just moving quickly to colorectal cancer. Agena also offers a panel for colon cancer, following the same principle than the lung cancer panel. I don't want to go too much into detail here, but it follows the same principle, which is starting from a single multiplex PCR reaction and having the same limit of detection. That is the sensitivity down to 0.1%. Actually, and we are able to detect more than 100 important and recommended markers from that single PCR. There's one study that I want to really bring to your attention because it has a lot, it shows a little bit of the potential that liquid biopsy has when comparing it to standard of care, the standard of care for metastatic colorectal cancer patients. So in this study, we were taking blood from, we were getting blood from patients that underwent chemotherapy, and the blood sample was taken at 3 time points. One was before the therapy started, one was after 1 cycle of chemotherapy, and then the 3rd time point is after completion. And at the same time, the patients were monitored by conventional imaging. So what you see here is that using the ultra-C colon panel for that example patient number 6 in that study, we were able to detect at time point number 1 at the left-hand side of the upper panel a KRAS mutation at an allelic frequency of 1.9%. That's the red line. That is dropping to 0.6% after 1 cycle of chemotherapy, and then dropping towards the right-hand side to not detectable. And a very similar, but at lower abundance, a very similar behavior for an NRAS mutation. Well, comparing these liquid biopsy findings to the imaging, which are the two images in front of the black background, number 1 and 2, where you barely see a difference in the images, whereas with liquid biopsy we could already see an effect of the treatment. So this dynamic is simply missing in the imaging, in the PET scan, and only at the third time point you could also see that then there was no tumor detectable anymore. So that's confirming the liquid biopsy. But in this study we could also validate the findings and cross-validate one technology with the other using digital droplet PCR, specifically looking for that KRAS marker, where in time point 1 we see that higher tumor burden than in time point 2, and again here in time point 3, then the KRAS marker, the mutation was not detectable anymore. So studies like that, and I'm actually coming to an end, so we have some time for questions. But studies like that really, are, I mean, interesting because not just because of the scientific meaning of it, but companies like Philips, for instance, being a big provider in medical devices and being a leader in the imaging field. They started a European-wide project where liquid biopsy and imaging will be compared and will be bundled. So so they are looking for a synergy between liquid biopsy and imaging, knowing that liquid biopsy testing will have opportunities and will play a role in future cancer care. So that project is called the LIMA. Stands for Liquid Biopsy and Imaging for Improved Cancer Care, and this project has started with a pretty high fund of more than 6 million euros just at the beginning of this year. Well, and to its prestige, it was announced certainly by Philips and by GenomeWeb. That is one consortia playing in the field of colorectal cancer and breast cancer. Another consortium I want to bring to your attention is also a European consortium. It's called the Cancer ID, that deals with also breast cancer, but also non-small cell lung cancer, and that is a mainly academic-driven consortia. You see on the map of the right-hand side, the Europe map of the right-hand side, you see where the academic partners are located across Europe, and the mission of that consortium is it's cancer treatment and monitoring through identification of circulating tumor cells and tumor-related nucleic acids in blood. So the aim really is to bring a liquid biopsy test into clinical routine by the end of the project. So with this, I just want to give a brief overview about where liquid biopsy can be applied today and maybe not yet today. Well, if we think about early detection, this may still be a little early. So detecting any cancer would require an enormous big panel. But however, you can already use liquid biopsy, for instance, for measuring or for detecting micrometastasis, relapse after surgery, for instance, or in certain cases, like demonstrated by Dennis Lowe, for instance, on so Epstein-Barr virus screening in blood can help to prevent and identify cases of nasopharyngeal cancer. So that is one of the cases where detection and screening can already be applied. But certainly liquid biopsy plays and can play a big role in treatment monitoring, whether it's by just detecting the sheer tumor burden, or looking for, as we've seen today, for specific response markers or resistance markers, or you can think about a follow-up, for instance, for a minimal residual disease. So as a summary today, we learned about, well, the limitations of tissue biopsies and the opportunities that liquid biopsy can give us. actually gave you an introduction on what is liquid, or how liquid biopsy is defined, and why it's important to think about the abundance of circulating DNA. Then take pre-analytical requirements into consideration, including a proper QC method. We've gotten a technology overview that certainly was not complete. We've seen some clinical applications that are highly interesting and fascinating. There's a lot of activity in consortia working and dealing with liquid biopsy. And then we saw some applications of liquid biopsy that are being used today. So with this, I want to thank for your attention, and would like to hand back to Christy at GenomeWeb for opening for questions.
Thank you, Dr. Sartori. As a reminder to webinar participants, if you do have a question, please type it into the Q&A box in the control panel. And before we begin the Q&A, we'd like to ask attendees to give us feedback by taking our exit survey after the webinar. And we'll now start the Q&A. Our first question, Alex, when a cfDNA sample is contaminated with genomic DNA, could a bead size selection be used to capture cfDNA only?
Well, that is an interesting idea. Well, we haven't actually, honestly, I don't know. I think this could be done, but I'm not aware about that. Well, that would be interesting to actually find out. Good question.
And have you checked whether different size fragments are recovered with the same efficiency by an isolation kit?
Well, sorry, can you repeat the question, because I just had trouble hearing that.
Have you checked whether different size fragments are recovered with the same efficiency by the same isolation kit?
No, we haven't tested that. We haven't tested that. As I mentioned earlier, we rely basically at Agena and in our role, we rely on samples that we do a lot of collaborations with samples that we're getting through collaborations, and it is actually very difficult to obtain liquid biopsy samples for doing a lot of research about these things. It is also a very interesting approach, but we haven't done that at Agena.
Can you enrich samples using a technique like PCR in order to increase sensitivity?
There is, there are approaches like allele-specific PCR that you could think about. We walked away from that because we think it generates a bias that you don't want to have. But basically, in order to achieve a higher sensitivity, I'm convinced at the level of PCR, more improvements can be achieved.
You mentioned that sensitivity is lower for next-generation sequencing than ddPCR and mass spec, but what about molecular barcoded amplicon NGS?
Yeah, I mean, the technology overview that I was giving was certainly not exhaustive for various options and development in NGS, and I'm aware that the molecular barcoding can increase the sensitivity, but I'm certainly not qualified to answer properly about that technology. So I would certainly like to refer back to the colleagues at these providers.
What is the maximum amount of targets and samples that can be run on the MassARRAY system?
Well, technology-wise, there's no limitations. However, in order to be cost-efficient, we would recommend. So, for instance, the panel that we've just seen and that I presented would allow you to run for liquid biopsy 8 samples on a single chip with this breadth of markers. But you could certainly do more, but then you would need more space, so you would need another chip, and that would certainly increase your cost. So, technology-wise, there's no real limitations on the on the efficiency side, I'd say between 50 and 150 markers are a good compromise.
And which technology do you think the liquid biopsy market is moving towards? Next generation sequencing, mass spec, ddPCR, or something else altogether?
Being a representative of Agena Bioscience, I should probably not answer that question. You can imagine where I feel and hope it's going towards, but well, I'm more than biased.
All right, thank you very much. I'm afraid that's all the time we have for today. We'd like to thank Alexander Sartori and our sponsor, PerkinElmer. If we didn't have time to get to your question, we will try to follow up with our expert. As a reminder, please look out for our pop-up survey after you log out to provide your feedback. And if you missed any part of this webinar or wish to listen to it again, a link to an archived version will be emailed to all attendees. Thank you for joining us for this Genome webinar.